Introduction.
Today we will fly the kite. We'll have fun.
Yes, my son.
Yippee! The kite is in air. How the kite flew in the air?
There are many forces which act on the kite, and these forces have specific directions, due to which the kite gets in the air.
But Dad, how do we define the direction of the forces acting on the kite?
Good question, my son. We define it with the help of vectors. Would you like to know more about it?
Yes, Dad.
In this lesson, you will learn the operations on vectors. Objectives. At the end of this lesson, you'll be able to differentiate between scalar and vector quantity, define position vector, find direction cosines of the position vector, find additions of vectors, find components of a vector, state section formula for internal and external division, find dot product of two vectors, find cross product of two vectors. Some basic concepts. A quantity which has only magnitude and not direction is called scalar quantity. For example, mass, temperature, etc. Let M be a straight line extending indefinitely on both sides. 2 points A and B on the line AB are forming the line segment AB. We can associate two directions with the line segment AB, that is from A to B or from B to A. Thus, the line segment AB with fixed direction from A to B or from B to A becomes a directed line segment with A as its initial point and B as its end point or terminal point. Such a directed line segment represents a vector and is denoted by vector AB or vector A. Practical example of vector. Thus, every vector has three characteristics, that is, 1. Magnitude, 2. Direction, and 3. Support. Acceleration, velocity, force, and displacement are all examples of vector quantities. Important points. The length AB is called the magnitude of vector AB and is denoted as mode of vector AB or mode of vector A. The direction of vector AB is from A to B. The line M of which the vector is a part is called the support of vector AB. Vectors AB and BA have equal magnitude and same support but have different directions. Some basic concepts. Position vector of a point. Let O be a fixed point in space called the origin of reference and P be any point whose coordinates are x, y, z such that vector OP is equal to vector r. Then the vector r is called the position vector of the point P. The magnitude of the vector r is given by mode of vector r equals square root of x square plus y square plus z square. Direction cosines. If alpha, beta and gamma are the angles subtended by position vector r with the positive direction of x, y and z axes respectively are called direction angles. The cosine value of these angles, that is cos alpha, cos beta and cos gamma, are called direction cosines of vector r and they are denoted by L, M and N, where L equals cos alpha, M equals cos beta, N equals cos gamma. Direction cosines are bound such that -1 less than or equal to L less than or equal to 1, -1 less than or equal to M less than or equal to 1, -1 less than or equal to N less than or equal to 1. And they are connected by the formula L square plus M square plus N square equals 1. From the figure we can find that cos alpha equals x by mode of vector r, cos beta equals y by mode of vector r, cos gamma equals z by mode of vector r. Types of vectors. Zero or null vector. A vector which has the same initial point and terminal point is called a zero vector or null vector and is denoted by vector 0. Vectors AA, OO, BB, all are zero vectors. Unit vector. A vector whose magnitude is unity is called a unit vector. For a given vector A, the unit vector in the direction of A is denoted by cap A and is given by cap A equals vector A by mode of vector A. Co-initial vectors. Two or more vectors are said to be co-initial vectors when they have the same initial points. For example, vectors AB, AC, AE, and so on are co-initial vectors. Collinear or parallel vectors. Two or more than two vectors are said to be collinear or parallel when they are parallel to the same line, irrespective of their magnitude and direction. Equal vectors. Two vectors are said to be equal if they have same magnitude, same direction, and same or parallel line of support. If two vectors A and B are equal, then they are written as vector A equals vector B, and they have same magnitude, that is, mode of vector A equals mode of vector B. Negative of a vector. Let vector A be a given vector, then the vector which has the same magnitude as vector A but is opposite in direction to that of vector A is defined as the negative of vector A and is denoted by minus vector A. Example. What is the direction of the vector in the figure given? Solution. The direction of the vector is 43 degrees east of south or 47 degrees south of east. Addition of vectors. Triangle law of vectors. If two vectors are represented in magnitude and direction by the two sides of a triangle, taken in order, then their sum is represented in magnitude and direction by the third side of the triangle, taken in opposite order. In triangle OAB, if vector A represented by OA and vector B represented by AB, then their sum, vector A plus vector B, is defined to be a vector represented in magnitude and direction by OB, where OB is the third side of the triangle OAB. In vector notation, we can write, if vector OA equals vector A and vector AB equals vector B, then vector OB equals vector A plus vector B, or vector OA plus vector AB equals vector OB. Parallelogram law of vectors. If two vectors are represented in magnitude and direction by two adjacent sides of a parallelogram, then their sum is represented in magnitude and direction by the diagonal of the parallelogram, which is co-initial with the given vectors. Symbolically, if vector OA equals vector A, vector OC equals vector B, then vector OA plus vector OC equals vector OA plus vector AB equals vector A plus vector B equals vector OB. Therefore, vector OC equals vector AB. Also, since vector OC is equal to vector AB, which equals vector B, vector CB is equal to vector OA equals vector A. Hence, vector OC plus vector CB equals vector OB. Addition of vectors. Properties of vector addition. Property 1. Vector addition is commutative. That is, vector A plus vector B equals vector B plus vector A. Property 2. Vector addition is associative. Here vector R is equal to vector A plus vector B plus vector C, and vector R is equal to vector A plus vector B plus vector C. Hence, vector A plus vector B plus vector C is equal to vector A plus vector B plus vector C. Multiplication of a vector by a scalar. Suppose vector A is any vector and n a scalar. By vector NA we mean a vector whose magnitude is mode of n mode of vector A. That is, n times the magnitude of vector A, and whose direction is that of vector A or opposite to that of vector A, depend upon that n is positive or negative. If n is equal to 0, then 0 vector A is equal to 0. Important results. Mn vector A equals M into n vector A. N into vector A plus vector B equals n vector A plus n vector B. M plus n into vector A equals M into vector A plus n into vector A. Components of a vector. Let P be any point in space with coordinates x, y, z. Then coordinates of the points A, B, C are x, 0, 0, 0, y, 0, 0, 0, z respectively. Suppose now that position vector of P is vector r. That is, vector OP equals vector r. Also, let cap I, cap j, cap k be the unit vectors along the three coordinates axes. Now OA equals x. It implies vector OA is equal to x cap I. Note that x cap I is a vector whose magnitude is 1 into x equals x and whose direction is that of the x-axis, and this is precisely the vector OA. Similarly, vector OB is equal to y cap j. Vector OC is equal to z cap k. From the triangle OPQ, vector R equals vector OP equals vector OQ plus vector QP equals vector OQ plus vector OC. Also from the triangle OAQ, vector OQ equals vector OA plus vector AQ equals vector OA plus vector OB. Thus, vector R equals vector OA plus vector OB plus vector OC. Vector R equals x cap I plus y cap j plus z cap k. Hence, if P is any point with position vector R and coordinates x, y, z, then vector R is equal to x cap I plus y cap j plus z cap k. X, y, z are called the components of the vector R. Mode of vector is square root of x square plus y square plus z square. Example. Find the unit vector in the direction of vector A equals 4 cap I minus 8 cap j minus 7 cap k. Solution. The unit vector in the direction of vector A is given by cap A equals vector A upon mode of vector A. Now, mode of vector A equals square root of 4 square plus minus 8 square plus minus 7 square equals square root of 16 plus 64 plus 49 equals square root of 129 equals 11.35. Unit vector is unit vector A equals 1 by 11.35 into 4 cap I minus 8 cap j minus 7 cap k. Unit vector A equals 4 cap I by 11.35 minus 8 cap j by 11.35 minus 7 cap k by 11.35. Assessment. Before proceeding further, let us know how much have you learned. Match the following. Multiplication of a vector by a scalar. Vector joining 2 points. The vector connecting point A to point B is given by vector R equals xb minus xa cap I plus yb minus ya cap j plus zb minus za cap k. The magnitude of the vector R is given by magnitude of the vector R is square root of xb minus xa whole square plus yb minus ya whole square plus zb minus za whole square. Multiplication of a vector by a scalar. Section formula. Internal division. If vector A and vector B are the position vectors of 2 points A and B, then the point C, which divides AB internally in the ratio m:n, has the position vector vector C equals m into vector B plus n into vector A by m plus n. Hence, the position vector of the point C, which divides A and B internally in the ratio of m is to n, is given by vector OC equals m into vector B plus n into vector A by m plus n. Corollary: if C is the midpoint of AB, then m equals n, and therefore the midpoint C of vector AB will have its position vector as given below. Vector OC equals vector A plus vector B by 2. Vector OC equals vector OA plus vector OB by 2. Vector OA plus vector OB equals 2 vector OC. External division. If A and B are the position vectors of 2 points A and B, then the point C, which divides AB externally in the ratio m is to n, has the position vector vector C equals m into vector B minus n into vector A by m minus n.
Example: find the position vector of a point R which divides the line joining the points whose positive vectors are P minus 2 cap I plus cap J minus 3 cap K and Q cap I plus 2 cap J minus 2 cap K in the ratio 3:1, 1 internally, 2 externally. Solution: 1 internally. The position vector of point R which divides the line joining the points P and Q in the ratio m is to n is vector OR equals m vector B plus n vector A by m plus n. Here m is equal to 3, n equals 1. Vector A equals minus 2 cap I plus cap J minus 3 cap K. Vector B equals cap I plus 2 cap J minus 2 cap K. Therefore, vector OR equals 3 into minus 2 cap I plus cap J minus 3 cap K plus 1 into cap I plus 2 cap J minus 2 cap K by 3 plus 1 equals minus 5 cap I plus 5 cap J minus 11 cap K by 4, which is equal to minus 5 cap I by 4 plus 5 cap J by 4 minus 11 cap K by 4. Externally, vector OR is equal to m vector B minus n vector A by m minus n. Therefore, vector OR is equal to 3 into minus 2 cap I plus cap J minus 3 cap K minus 1 into cap I plus 2 cap J minus 2 cap K by 3 minus 1 equals minus 7 cap I plus cap J minus 7 cap K by 2 equals minus 7 cap I by 2 plus cap J by 2 minus 7 cap K by 2.
Product of two vectors. Scalar or dot product of two vectors. The dot product of two vectors A and B is magnitude of A times the magnitude of B, then multiply the cosine of the angle between A and B, where theta is the angle between vector A and B. Important points. If vector A and B are perpendicular to each other, then dot product of vector A and B is 0. If vector A and B are parallel to each other, then dot product of vector A and B is magnitude of vector A into magnitude of vector B. The unit vectors cap I, cap J, and cap K are perpendicular to each other, so their dot product is as follows. Cap I dot cap I equals cap J dot cap J equals cap K dot cap K equals 1. Cap I dot cap J equals cap J dot cap K equals cap K dot cap I equals 0. The dot product follows the commutative property. That is, dot product of vector A and B is equal to dot product of vector B and A. Dot product follows the distributive law of addition for the three vectors A, B, and C. Dot product of vector A and vector B plus vector C is equal to dot product of vector A and B plus dot product of vector A and C. If vector A is equal to A1 cap I plus A2 cap J plus A3 cap K, vector B equals B1 cap I plus B2 cap J plus B3 cap K, then dot product of vector A and B equals A1 B1 plus A2 B2 plus A3 B3, product of two vectors. Projection of a vector on a line. Let P be the foot of the perpendicular from A to the line OB. OP is called the projection of vector A on the line OB. Vector OP is equal to magnitude of vector A into cos theta, where vector A is equal to vector OA and theta is angle AOP. Important point. If theta is equal to 0, then the projection vector of OA will be vector OA itself, and if theta is equal to pi, then the projection vector of OA will be vector AO. Example. Find the angle between two vectors A and B with magnitudes 10 and 12 respectively, and when dot product of vectors A and B is equal to 5. Solution. The dot product of vector A and B, magnitude of A times the magnitude of B, then multiply the cosine of the angle between A and B. Cos theta is equal to dot product of vector A and B by magnitude of vector A into magnitude of vector B. Theta equals cos inverse dot product of vector A and B by magnitude of vector A into magnitude of vector B. Theta equals cos inverse 5 by 10 into 12. Theta equals cos inverse 5 by 120. Theta equals cos inverse 1 by 24. Theta equals cos inverse 0.04167. Theta is equal to 87.61 degree. Vector or cross product of two vectors. We have drawn the two vectors so that their tails are at the same point. The angle between the two vectors has been labeled theta. When we find a vector product, the result is a vector. First, we define the modulus or magnitude of this vector as magnitude of vector A into magnitude of vector B into sine of theta. To obtain a vector, we need to specify a direction. By definition, the direction of the vector product is such that it is at right angles to both vectors A and B. As stated in the figure, the convention is that we choose the direction specified by the right-hand screw rule. This means that we imagine a screwdriver in the right hand. The direction of the vector product is the direction in which a screw would advance as the screwdriver handle is turned in the sense from A to B. The vector product of A and B is defined to be vector A cross vector B equals magnitude of vector A into magnitude of vector B into sine of theta in the direction of n cap, where magnitude of vector A is the modulus or magnitude of A. Magnitude of vector B is the modulus of B. Theta is the angle between vector A and B, and cap n is a unit vector perpendicular to both vector A and B in a sense defined by the right-hand screw rule. Important points. Vector product of unit vectors which are perpendicular to each other is as follows. Cap I cross cap I equals cap J cross cap J equals cap K cross cap K equals vector 0. Cap I cross cap J equals cap K, cap J cross cap K equals cap K cross cap I equals cap J. Cap J cross cap I equals minus cap K cross cap J equals minus cap I cross cap K equals minus cap J. If vectors A and B represent the adjacent sides of a parallelogram, then its area is given by magnitude of vector product of vectors A and B. If vectors A, B, and C are three vectors, then vector A cross vector B plus vector C equals vector A cross vector B plus vector A cross vector C. If vector A is equal to A1 cap I plus A2 cap j plus A3 cap k, vector B equals B1 cap I plus B2 cap j plus B3 cap k, then vector product of A and B is equal to determinant of row-wise first row cap I, cap j, cap k, second row A1, A2, A3, third row B1, B2, B3. If vectors A and B represent the adjacent sides of a triangle, then its area is given as 1 upon 2 into magnitude of vector product of A and B. Example: prove that the vectors 2 cap I minus 3 cap j minus cap k and minus 6 cap I plus 9 cap j plus 3 cap k are parallel. Solution: the given vectors will be parallel if the cross product is 0. Now, 2 cap I minus 3 cap j minus cap k cross minus 6 cap I plus 9 cap j plus 3 cap k equals determinant of row-wise first row cap I, cap j, cap k, second row 2 minus 3 minus 1, third row minus 6, 9, 3, minus 9 plus 9 cap I plus 6 minus 6 cap j plus 18 minus 18 cap k equals 0. Hence proved. Assessment. Before proceeding further, let us know how much you have learned. Drag and drop the correct options. Did you know Sir William Rowan Hamilton came up with the concepts of scalars and vectors in 1843? William Rowan Hamilton's scientific career included the study of optics, classical mechanics, applying vector methods to problems in mechanics and in geometry. Summary. Let us summarize what we have learned. A quantity which has magnitude and direction is called vector quantity. Let O be a fixed point in space, called the origin of reference, and P be any point whose coordinates are x, y, z such that vector OP is equal to vector R. Then the vector R is called the position vector of the point P. Direction cosines are L equals cos alpha, M equals cos beta, N equals cos gamma, and they are connected by the formula L square plus M square plus N square equals 1. If two vectors are represented in magnitude and direction by the two sides of a triangle, taken in order, then their sum is represented in magnitude and direction by the third side of the triangle taken in opposite order. If two vectors are represented in magnitude and direction by two adjacent sides of a parallelogram, then their sum is represented in magnitude and direction by the diagonal of the parallelogram, which is co-initial with the given vectors. Mn vector A equals M into N vector A. N into vector A plus vector B equals N vector A plus N vector B. M plus N into vector A equals M into vector A plus N into vector A. The position vector can be represented as vector R equals x cap I plus y cap j plus z cap k. If vector R is connecting two points A, xa, ya, za, and B, xb, yb, zb, then vector R is equal to xb minus xa cap I plus yb minus ya cap j plus zb minus za cap k. If vector A and vector B are the position vectors of 2 points A and B, then the point C, which divides AB internally in the ratio m:n, has the position vector. Vector C equals m into vector B plus n into vector A by m plus n. If A and B are the position vectors of 2 points A and B, then the point C, which divides AB externally in the ratio m:n, has the position vector. Vector C equals m into vector B minus n into vector A by m minus n. The dot product of two vectors A and B is magnitude of A times the magnitude of B, then multiply by the cosine of the angle between A and B. where theta is the angle between vector A and B. The vector product of A and B is defined to be vector A cross vector B, which is equal to magnitude of vector A into magnitude of vector B into sine of theta in the direction of n cap, where magnitude of vector A is the modulus or magnitude of A. Magnitude of vector B is the modulus of B. Theta is the angle between vector A and B, and cap n is a unit vector perpendicular to both vector A and B in a sense defined by the right-hand screw rule.